That's good, buddy.
Yep.
Forgot we're not in high school.
Oops, this is going to be difficult.
So this is section 11.1. And so let me start out just with the definition. Okay, so
I don't have my notes out yet, Marks.
Mark Seaman.
there's a set of points x, y.
Oh, I thought I was filming the wall.
Equation. So it's a set of points of x, y. Which satisfy a pair of equations. Okay, satisfy the equations, say x equals f of t and y equals b of t. So x and y are both given in terms of a new variable t. Okay, you got x is some function of t and y is another function of t. Where t is in some interval. Okay, for all t in some interval. So in a parametric curve, x and y are given in terms of a new parameter, okay, t. Okay, so these are called parametric equations for the curve, and t is called a parameter. These are called parametric equations for the curve, and the variable t is a parameter. So let me look at a couple of examples. So let's look at some curves we can describe this way. So I'd just like to look briefly at a couple of examples like this. So as an example, suppose we took the following curve. Suppose we took a curve, say, given by x is equal to 4 cosine t and y equals 4 sine t, and we let t go from 0 to 2 pi. Okay? And so let's see what type of curve you get in this case. So one way to figure out what kind of curve you have is to solve these equations for sine t and cosine t, and then use the identity that cosine squared plus sine squared equals 1. So if you do that, if you solve this for cosine t, solve this for sine t, and then just use the cosine squared plus sine squared equals 1, you'll see that you get a circle. And so what this represents is just the circle, x squared plus y squared equals 16, like this. So the circle is the origin radius 4. And this curve is traced out once going counterclockwise. In other words, if you actually start plotting points, you'll see you start here when t equals 0, and when t goes from 0 to 2 pi, you go around the circle once counterclockwise, like that. And so this actually, gives us a useful way to represent this circle. So we'll see some problems later on where using this form for the circle instead of using x squared plus y squared equals 16 is actually more convenient. So this is actually a good way to describe the circle for some purposes. Okay? Let's take a look at another example of a parametric curve. So the next example I'd like to look at is one that's not so easy to describe without a parameter. Although you can do it, but it's not very easy to do. So the next example I'd like to look at is the following curve. Suppose we took the curve, say, x is equal to 3 times t minus sine t, and y is equal to 3 times 1 minus cosine t. And let's again let t go from 0 to 2 pi. Okay? And so let's take a look at what this curve looks like. Actually, let me just draw a rough sketch of this. So if we make a rough sketch of this curve, it'll look something like the following. Let's see, when t is 0, you have the point 0, 0. And when t is 2 pi, I guess you have the point 6 pi and 0. Like this. Okay? So it starts here, and then here, and let's see, when t is pi, I guess you get x is 3 pi and y is 6. So what you get is a curve that looks something like this. So this is a cycloid. And what this represents is the path that a point on a circle takes as the circle rolls along the x-axis. So if you have a bicycle tire and you paint a dot on the tire, and then watch the path of the dot as the person rides along the street, this is the path that it would follow. In other words, if you start out with a circle, let's see, I guess the circle, I guess, would look. Suppose we start out with a circle like this, and we paint a dot, on the circle. Then as we roll the circle to the right along the x-axis, this is the path that this dot will trace out. Okay, so that's another example of a curve that's given parametrically. We'll come back to this later on. Okay. Now, one thing I want to look at. The idea of a parametric curve generalizes the curve that we've already looked at. So if you take the curve y equals f of x, right, which is the most common type of curve we've been working with, you can represent this parametrically. So this can be written as, we can write this in parametric form as x equals t and y equals f of t. Okay? You can write this in parametric form like this. X equals t, y equals f of t. And similarly, if you have a curve where x is given in terms of y, which we've also been working with, suppose we have a curve x equals f of y. Okay? We can write this parametrically by letting y be the parameter. So here we can replace y by t. So we can write this as x equals f of t and y equals t. So in the first case, we're letting x be the parameter. For the second type of curve, we're just letting y be the parameter. So you can represent the types of curves we've been working with so far parametrically just by doing that. Let's see, before I go on, do you have any questions about what I said about parametric curves? We'll come back to this
Just pause it back.
later.
Yeah, so the gotcha, what's the step?
Can you guys pause that
This
back?
gives us a more general way to represent
Where
curves.
am I? Right here.
Now, what I'd like to do next is start talking about arc length. So let's take a look at how we can describe the length of a curve. So this is in section 11, section 6.3 and 11.2. And so suppose we have a curve and we want to figure out the length of the curve. Okay, so let me draw a parametric curve here. So let's say we have some kind of curve given parametrically. Say it looks like this. So let's let this be the curve x equals f of t and y equals e of t. Let's say t, goes from A to B. Okay, let's let this be a parametric curve.
87 to 112 is an A.
And I want to try to figure out the length of the curve. And we're going to make the following assumptions. So we're going to assume that f and g are both differentiable and they have continuous derivatives. So we're going to assume that f prime and g prime are continuous. So the derivatives exist and they're continuous. And never both 0. So this is what's called a smooth curve. So the curve is called smooth if the derivatives are continuous and never both zero. So we're assuming we have a smooth curve. Okay? And what I want to do is try to find the length of this curve. So this point, say, is the point f of a. Let me write this as the point corresponding to t equals a. Let me write this as the point corresponding to t equals b. So this is the point f of a, g of a. This is the point f of b, g of b, like this. So if we want to find the length of this curve, we'll use the following idea. First, we're going to cut this up into little pieces. That corresponds to taking a partition of this interval from a to b. So if we take a partition of the interval from a to b, that corresponds to cutting this curve up into little pieces. And then once we've done that, what we're going to do is just approximate each piece by a line segment. So we're just going to draw a line segment between each pair of points, add up the lengths of these line segments, and that'll give us an approximation for the length of the curve. And then what we'll do is take a limit as the subintervals get smaller and smaller. And that should give us the actual length of the curve. So to find the length of the curve, the basic idea is we break it up into pieces and approximate each piece by a line segment. So that's what we're going to do. So we can break it into small pieces and approximate each piece by a line segment. So that corresponds to taking a partition of the interval from a to b. So we're going to approximate each piece by a line segment. So let's look at the formula we get when we do that. So if we approximate each of the pieces by line segment, we'll get a picture that looks something like this. Okay? So when we do this, we'll have a picture that looks like the following. Let me just draw a small piece of the picture here. So let's say we have a piece of the curve, say that looks like this, and I'm going to call this distance delta s, where I'm going to use s for arc length. So that's going to be the length of that piece of the curve. And I'm going to approximate that length by this length of this line segment. And to find the length of this line segment, I can use the Pythagorean theorem. This is going to be the change in x, and this distance is going to be the change in y. And so if we let s denote arc length, we have that the length of a small piece of the curve, which is what I'm calling delta s. So that's the length of a small piece. That's approximately equal to the length of this line segment. And by the Pythagorean theorem, that's the square root of delta x squared plus delta y squared. Now, what I've written down here is really just the distance formula in disguised form. I mean, that's the formula, right, for the distance between 2 points. You just take the square root of x2 minus x1 squared plus y2 minus y1 squared. So here I'm just using the distance formula there. Okay, or equivalently the Pythagorean theorem. And now, so this is an approximation of the length of this piece of the curve. And then what we can do here is multiply and divide by delta t. So we can write this as the square root of delta x squared plus delta y squared. I'm going to multiply that by delta t. And I'm going to divide that by delta t. Now, since delta t is positive, I can write delta t as the square root of delta t squared, like that. And so I'm multiplying by delta t and dividing by it. And so we get the approximation that the change in the small piece of the curve that we're looking at, delta s, is approximately equal to, so the small piece of the curve has arc length approximately equal to the square root of delta x over delta t squared plus delta y over delta t squared times delta t. So that gives us an approximation to the length of a small piece of the curve. Okay. I'm just combining this right into one square root. So I'm just writing this as one square root in the first factor. So that's an approximation for the length of one part of the curve. So now what we want to do is add these up for each piece and take a limit as the norm of the partition of the interval from A to B goes to 0. And so, so this gives us, that the length of the curve is going to be an integral that you get by adding up these approximations for each subinterval and taking a limit. So the length of the curve is given by s is equal to the integral from A to B of the square root, and then I'm going to change all these deltas to d's. In other words, you get the square root of the derivative of x squared plus the derivative of y squared integrated with respect to t. So in the arc length formula, and when you take a limit, these deltas become d's, and you get a derivative inside the square root. So you have the integral from A to B of the square root of the derivative x squared plus the derivative y squared, all integrated with respect to t. Now, because of this square root, for most curves, you can't find the arc length exactly, and you have to use some kind of approximation technique. But there's, certain special curves where we can actually find the arc length exactly. Okay. Let's see. Let me just make a remark. Okay. In going from the delta x over delta t to the dx over dt, we have to use the mean value theorem. So, so the proof, if we actually wanted to give a rigorous proof, the proof uses the mean value theorem. Okay. So the mean value theorem is a key idea behind this formula. In other words, if you take delta x over delta t, right, that's equal to f of t sub I minus f of t sub I minus 1 divided by t sub I minus t sub I minus 1 for the ith subinterval, right, you get something like that. And by the mean value theorem, this is equal to the derivative f at some number c for some c between t sub I and t sub I minus 1. In this subinterval. So that's why you can replace delta x over delta t by this derivative. You're using the mean value theorem to do that. Let's see, before I continue, do you have any questions about what I've said so far about arc length? So the basic idea is you're just taking the curve, cutting it up into little pieces, and just approximating each piece by a line segment. And then to get the length of this line segment, we're just using the distance formula. That's all we're doing. Why don't we look at some examples, okay, of using this formula. So let's take some curves and actually find their length. Okay? So let's look first at the following example. So let's find the length of the following. So let's take the curve given by. So let's take the parametric curve. Say x is equal to sine t plus cosine t. Y is equal to sine t minus cosine t. And let's say t goes from 0 to 2 pi. T goes from 0 to 2 pi. And so let's try to figure out the length of this curve. It's not really clear exactly what kind of curve this is. Okay, the way it's written. So let's see if we can find the length. So to get the arc length, we want to take the integral from A to B. So in this case, that's 0 to 2 pi of the square root of the derivative x squared plus the derivative of y squared, right, integrated with respect to t. And so if we figure out our derivatives here, we have the integral from 0 to 2 pi. And so we have the square root of, so the derivative x, right, is going to be cosine t minus sine t. So we get cosine t minus sine t squared. And then if we take the derivative of y and square that, we'll get cosine t plus sine t squared. And then this is all integrated with respect to t. Okay, so we get something like that. So now we have to simplify right with underneath the square root. Does that look all right so far? What we've done? So now let's just multiply out what we have right underneath the square root. Let's see what we get. Okay, so we have that the arc length is equal to the integral from 0 to 2 pi. And so we have the square root of, so we'll get cosine squared t minus 2 cosine t sine t plus sine squared t. And then in the second term, we'll get almost the same thing, right? We'll get cosine squared t plus 2 cosine t sine t plus, so we get plus sine squared t, and then this is all dt, when you're at the dt down here. Okay, like that. Okay. So now, right, we can cancel the two middle terms. Right, those just cancel, and now we can combine the cosine squared plus sine squared, right, gives 1. And similarly, like this cosine squared plus this sine squared gives 1 as well. So what we're left with, once we simplify, is the integral from 0 to 2 pi of the square root of 2. I think you get something like that. Okay? Because cosine squared plus sine squared is 1, and so we have 1 plus 1 or 2 underneath the square root. So now we can just pull the square root of 2 out in front, and we get square root of 2 times the length of this interval. So we get square root of 2 times 2 pi. Right? So we get 2 square root of 2 times pi. So that's the length of that curve. You might want to see if you can figure out what kind of curve that is, if you get a chance. Do you have any questions on what we did in that problem? Let's use the formula to find the length of another curve. So let's look next at the following. Let's take the curve given by. So let's look at the curve given by x is equal to 1/3 t cubed.
1 plus 1.
Does that look okay what we got in the last example? We have x equals 1/3 t cubed, y equals 1/2 t squared. And let's say t goes from 0 to let's say 3. Okay, let's try to find the length of this curve. So if we use our arc length formula, we have that the arc length is going to be the integral from 0 to 3 of the square root of the derivative x squared plus the derivative y squared. And so in this case, right, the derivatives are easy to figure out. We get the integral from 0 to 3 of the square root of, so the derivative of x is going to be t squared. So we get t squared squared, and then derivative of y is just t. So we get plus t squared dt. Okay, so I think we get something like that. And so we have the integral from 0 to 3 of the square root of t to the 4th plus t squared. And what would be a good thing to do next? Yeah. Now let's factor out a t squared. That's right. Right? That's right. If you factor out a t squared, you get the square root of t squared times the square root of t squared plus 1. Okay. And now keep in mind, right, in general, the square root of t squared is the absolute value of t. But in this case, right, we're looking at positive values of t. Right? So in general, this would give us the absolute value of t, but here t is positive. So we can just write this as the integral from 0 to 3 of t times the square root of t squared plus 1. So once we have that, right, now we can make a use substitution. Right, we can just substitute for t squared plus 1. And if we do that, right, then du is going to be 2t dt. And if we look at our new limits, right, if t equals 0, we get u is equal to 1. So if t equals 0, u equals 1. And if t equals 3, u equals 10. So if t equals 0, u equals 1. And if t equals 3, u equals 10. So if we rewrite our integral, we have 1 half the integral from 0 to 3 square root of t squared plus 1 times 2t dt. So I'm multiplying by 2 on the inside, divide by 2 out in front. And now we can write this in terms of u. Right? In terms of u, we have 1 half the integral from 0 to 10 of the square root of u du. And right now we can use the power rule to integrate because we have 1 half times the integral from 0 to 10 of u to the 1 half. So we get 1 half times 2/3 u to the 3 halves. Okay, so we add 1 to the power and divide by the power. That we get 2/3 u to the 3 halves from 0 to 10. And so now if we substitute in, we'll get 1/3 times 10 to the 3 halves. We take the 3, okay, times 10 to the 3 halves. And then the value of 0 is 0. So we could write our answer like this, or if you want, you can write it 1/3. Right, you write it 10/3 squared. Oh, it's from 1 to 10? Yeah, I'm sorry. It is. That's right. Thanks. This would be from 1. Okay, let's see. So that was good. So if we factor out the 1/3, we have 1/3. So this will give 10 to the 3 halves minus 1.
Oh, shoot.
Like that.
That is hard.
You have any questions about anything in this problem? So this is the basic formula we can use in general. So if I give you, if we're given any type of curve, we can use this. And if we're given y in terms of
8,
x,
16,
or x in terms of y,
17,
we
18.
can just
But there's,
write it in parametric form
oh,
first.
it's the
and then
2
use
counting
the formula
those
if we
2.
want. Okay? But what I'd like to do next is to look at the special cases. You can you can always use this formula, okay, for a curve given parametrically, or when y is given in terms of x, or vice versa. But let's look at the special
I didn't know
cases
how to do that
we
one.
can get if we want, where y is given in terms of x, or x is given in terms of
What
y.
would it be?
So
I didn't know how to do that one.
let's look first of all
This
where
one's
y is
awesome.
given in terms of
That
x.
one. I got 2 points.
So for the curve y equals f of x,
This one.
so one way we can handle this
That's
is just write it in parametric
So I
form.
did pretty
We
good.
can write x equals t and y equals f of t, and then just use the general formula. But if we let x be the parameter, in other words, replacing t by x gives the following formula.
I always just make stupid
So if we
mistakes.
replace t by x in the general formula that we have there, that gives that the arc length for a curve of this type is going to be the integral from a to b, and then we have the square root of the derivative x with respect to itself squared, so that's going to be 1, plus, so I'm just replacing all that t by x. So you get the square root of 1 plus dy dx squared integrated with respect to x. Right, so if you replace t by x in the general formula, you get a formula like this. So that's how you can find the length of a curve where y is given in terms of x. You're just replacing the parameter t by x in the formula. And similarly, we can do the same thing if we have x given in terms of y. So let's see what we get if we do that. So if we have a curve x equals f of y, we can just replace t by y. So if we have x equals f of y, we can either write this in parametric form by letting x equal f of t and y equal t. But the other thing we can do is just replace, just replace t by y in the general equation. So if we replace t by y, that gives the following formula. So if we go back to that formula and replace t by y, we'll get the arc length is the integral from a to b of the square root of dx dy squared plus 1 squared. Let me just write the terms in the other order. Like this. You get the square root of dx dy squared plus 1 squared integrated with respect to y. So you're just interchanging the roles of x and y in the first. So those are the formulas you can use if you want when y is given in terms of x or x is given in terms of y. Yeah. Oh, why did I divide delta x by delta t? Yeah. In other words, so that's the approximation we got by using the distance formula. And then if you take delta x over delta t, so that's the first expression, the square root. If you write that out and use the mean value theorem, you get that delta x over delta t is the derivative of x. Right? X is f of t. So this is the derivative of x with respect to t at some number. So this is sort of the justification for going from delta x over delta t in the approximation to this expression. That delta x over delta t is actually the derivative x at some number. So that's sort of the idea behind replacing that by a derivative. But delta x over delta t, right, was just a horizontal. That was just the base of the triangle that we had. And delta y over delta t, I'm sorry, delta x is the base of the triangle, and delta y was the height of the triangle. Okay, that we drew in approximated by a line. Let me take a look at some examples of using these formulas. Okay, so let's look at the following.
I was thinking that this song is going to be too big to send. I'm just going to upload it to YouTube and send the link. Oh wait, I'm going in the wrong board.
Of the curve given by y is equal to, let's say, x to the fourth over 4 plus 1 over 8x squared. X to the fourth over 4 plus 1 over 8x squared, where x goes from 1 to 2. So I'm going to find the length of this curve. So one way we can do this is just let x equal t, and let y equal t to the fourth over 4 plus 1 over 8t squared, and then just use the general formula. Okay, but let me just, probably a little bit simpler.